get more and more circular, you distribute the mass more evenly around the orbit until the force at pericenter becomes important and starts stabilizing you.
Right, I guess I'm just curious if that 0.6 comes out of the theory, or?
Yes. Yes, with a lot more work. And looking numerically at the problem, not just kind of using my hands. The 0.6 actually does drop out, that you should be stable below roughly 0.6 and unstable above 0.6. Okay. So I want to get us situated where I think this is important. So this is our solar system, obviously. This is a semi-major axis as a function of eccentricity, and these are Earth and the giant planets. Pluto has a significant eccentricity, but it doesn't count because it's not a planet. It's part of the Kuiper belt. But I'm more interested in bodies that are further away. So Neptune is at about 30 AU. I'm interested in trans-Neptunian objects, but starting around 100 AU. So why is that? So Neptune and other giant planets, particularly early on in the formation of the solar system, scattered a lot of bodies out. Small mass bodies we think formed closer to the sun, but came into contact with the giant planets and got scattered outwards. When you scatter outwards, but you scatter at your perihelion, you have to conserve roughly your perihelion distance. Can go into that if anybody wants to talk about that more. So if you're scattered outwards, you have to get more eccentric. And this is why we have something called the scattered disk in the outer solar system. These are bodies that are actually still in contact with Neptune, meaning at some point in their orbit they can get close to Neptune and get a good strong kick again. But they all show this structure. As they move outwards, they're more eccentric. And they all have a perihelion that puts them in contact with Neptune. It tells us that they once scattered off Neptune. This is why they're here now. So we understand them really well. It was first shown theoretically in N-body simulations, yay. Not by me, but yes, simulations. And then discovered observationally. But that's all very well understood. That's not very interesting. What is really interesting is a population called detached objects. So these are objects that, maybe, I don't think we need to turn on a light, I'll draw this thing. So if this is Neptune's orbit at 30 AU, a scattered disk object will have an orbit like this. It's got a high enough eccentricity so that its perihelion brings it close to Neptune. A detached object is an object that might have a similar semi-major axis, maybe a little higher, but its orbit is like that. So it's too circular. At no point on its orbit does it come close to interacting with Neptune. So how did it get there? That's the question. And there's other weird things about these detached objects too. So why did I bring up this Kepler element omega? In 2014, Trujillo and Shepard, they discovered 2012 VP113. Its nickname is Biden, because Biden was VP at the time. By the time it actually gets named, I don't think anybody's going to call it its real name. Everybody calls it Sedna Biden. It's just, that's what we say now. Okay, sorry, but so they discovered Biden, which is a very similar object to Sedna, very low mass, very detached, very interesting object that's floating in the middle of nowhere. You see the semi-major axes are really large. What they noticed in this paper is that if you plot their omega values, this is something to do with the orientation of the orbit in space, to do with its pitching and rolling, they don't seem to be randomly distributed once you get above about 150 AU. So this is really unusual, because a scattering process should not give you a preferential value for your omega, or like how you're pitching and rolling relative to your initial plane that you started off with. And this is plotting all the bodies with semi-major axis, or perihelion distance greater than Neptune here. Okay, so this set off a huge eruption in the outer solar system side.
Is that the evidence that people were worried about? Okay, there's a little bit more below than above, but how significant is it?
So
a few objects.
Yeah, so now we have about 23.
Okay.
objects, yes. But that is very interesting question, and there are two camps. It is not significant, and it is hugely significant.
Okay, which one are you?
I'm more in the, I hope something interesting is going on out there, but
That's
there's there's so many observational biases,
Yeah.
and it's really taken over the field. But taken together, okay, so I'm not going to show you plot after plot of all the different observational evidence for something odd going on in the outer solar system. Let me just kind of list them here and move on, because this is only one part of the talk as well. But the weird things, I think the first one is completely uncontested. There's something odd in the fact that we have bodies that are detached from the solar system, meaning they never come close to a massive body. So how did they get there, right? We don't think they formed there, they had to get out there. Something had to happen to their orbits. Particularly if they formed in the scattered disk, then all of a sudden their orbits had to circularize, which is odd. I didn't show you a plot of this, but some are extremely highly inclined. One recently was discovered, I'm going to forget its name, its nickname, obviously. But it's
maybe?
I don't know what it says about the politics in astronomy, but nobody's called a body Pence. But this body has an inclination of 60 degrees with respect to the midplane of the solar system. And this is even more interesting when you realize that there's so many observational biases. If we want to find outer solar system objects, what we've been doing for a long time is staring at the ecliptic. Let's stare, or the invariable plane. Stare at the plane of the solar system, because that's where things formed. So to find extremely inclined objects in these surveys is unexpected. And now, of course, what I'm very excited about is we're starting to look higher and higher. Like, yes, keep going. There's clustering in Omega, two camps. It's very significant, it's not remotely significant, and observational biases can explain everything. And the fourth point that I don't want to dwell on too much, because there's even more observational biases on this one, but there's clustering in an angle that looks very much like Omega. For people who deal with Kepler elements, you know everything is called Omega for some reason, capital Omega, little omega, or pomega. But this is a clustering in eccentricity vector space. So are the orbits all randomly distributed in roughly a disk, or are they all pointing on one side of the sky? So this last one has really motivated the Planet 9 hypothesis. Okay, so I think everybody will know what I mean by Planet 9, but just to show you what I mean here. So these purple or magenta lines are the bodies that are the most stable that we've discovered, and really that translates to the bodies that have the largest semi-major axes and really aren't interacting with the giant planets at all. I'm plotting their orbits. So there were fewer of them, and this is also back in 2016, but you'll see definitely there seems to be some orbital clustering. This is Pomega clustering in particular. What Mike Brown and Konstantin Petitkin showed is that if you put a ninth planet in the outer solar system that would have 10 Earth masses, it has to be very eccentric, very highly inclined, something like 30 degrees with respect to the midplane of the solar system. The gravitational forces from this giant planet will shepherd the orbits into this configuration, the smaller mass orbits. So it works really, really well. The only problem is you have to go find this planet, or it's just a theory.
Also, how did it get there?
Exactly. Yes. Also, how did it get there? Right? We don't think we form planets out there. You can scatter a planet outwards, like variations on the Nice model. They put 5 giant planets and one gets scattered out. But how do you scatter it out to this location and change its orbit so that it's not that eccentric anymore, so that it can remain hidden in the outer solar system for a long time? That's actually statistically really difficult to do. You can also try and capture it from another star. There's really loads of fun ways, but if you add up the probabilities, it's still really, really difficult to explain. But if it's there, it's fantastic, because it's really exciting. For everybody but me, obviously, because I have a different theory. But I would still actually be really excited if Planet 9 exists. But to wrap up this part of the talk, maybe this is a surprise to some of you, or maybe this is really obvious that this is where I was leading. If you have bodies in the scattered disk on really eccentric orbits, and you let them gravitationally interact with each other, with no Planet 9, this is exactly what they will do. They detach. I mean, they incline off the plane, they become less eccentric, so they detach themselves, they become more circular, so they're no longer touching the giant planets. They cluster in omega, you don't need to do anything about that. And finally, when I've given this talk before, I crossed this out and said, this is probably observational bias, let's just ignore this. But there was a recent paper that promises that if you include the presence of the giant planets that causes extra precession in your system, you can actually start clustering your minor planets also in this Pomega value. So I haven't seen it, the paper isn't out, but it's an interesting thing. You could actually start just through the self-gravity of these bodies themselves, clustering them onto one side of the sky, yet to be seen.
So in your simulations it didn't happen, is that right?
I haven't, oh no, in my simulations, no. You get clustering in omega,
Omega, right.
and to be honest, I don't see how you can have both.
Okay.
But there's a promise
Okay.
that it can collapse into this kind of more one-sided structure. And that, as I'll show you soon, is really stable. But I don't see how you could get both omega clustering and pomega clustering at the same time. And the observational biases are, and the conversation right now is so hectic with the observers that I don't know which one I trust more. Anyway, but this is not, you get it for free, there is no Planet 9 and we'll go home.